All right, welcome, people on the internet. Um, Two people on the internet. Welcome.
Hey, the three of us are on the
What
internet.
about us?
Yeah.
Yeah, all
I
right.
am currently residing in the cyberspace.
Oh,
It's a momentary uh, interaction with the because that's the stream. That's the stream. That's the moment.
Sweet.
Yeah. All right. Yeah. Hello. This is hello. 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 My name is Dan Reynolds. If you did not know, there you go. And this is the Tech Audio Chat that where we do tech audio stuff and/or talk tech audio stuff and/or just be tech audio, focused people
Hang
in a
out.
chat. Yeah, exactly. I currently work at Epic Games as a technical designer, for what it's worth, and
wow.
I'm joined. I'm joined by. Sorry, I'm not very good at forms. I find proprietary a little silly. I'm joined by Eric Buchholz. I'm Aaron McLeran, and a new face, David Weaver.
Hello, hello.
Welcome, David.
Welcome. And actually, this could be a little bit of. Actually, so first of all, David, you actually have a pretty active YouTube yourself.
There's a channel that's supposed to have a video that doesn't have one for this month yet, but yeah, no, I do some YouTube stuff very much inspired by yourself on primarily Unreal Engine audio, even though I'm not an Epic Games employee. But there's so much to find in this engine that occasionally we stumble into something that we both don't know about. So
Yes,
it's one
well,
of those
that's every day. Yeah.
yeah. Yeah, so check it out. Weaver Audio, I think it's D Weaver Audio on YouTube. And it does, tech audio implementation, audio programming, audio tool set stuff, and walkthroughs of new epic things.
Yeah.
I learn
David-
stuff from your channel all the time.
Yeah.
So
Yes.
It's kind of a weird
Yes.
Ouroborosian thing. Like we make tech. By the way, I'm the Unreal Engine director of our audio tech. So David will, make some tutorial on some of the tech that we're making, and I'll watch the tutorial and go, oh, that's an interesting angle or take or that kind of a thing. It's kind of fun actually.
Well, sometimes it's fun to make it wrong as well. Like you make it in a way that it just sort of
Unintended.
fits your project, and then someone else is like, "Oh no, we couldn't do it that way because our project used an isometric camera and it didn't work that way, and the feature's actually for this other thing entirely." And I'm like, "Oh, sorry, yeah, no, I'll make another one."
It's a good way to invite my comment.
Yeah.
Yes, yeah, that's for sure. They're definitely, if I ever make something, I can just make a bunch of things that are wrong, and Dan will be in the comments being like, a few
Well,
things.
actually,
I'm not.
I try to do it in DMs. Like I'll DM a content creator and be like, "Hey, yeah, this thing you said it's not exactly that."
very
Rather than publicly calling him out. I try at least. I don't think I've ever done that for you, David. Have I ever corrected you in a DM?
I'm not
corrected,
sure.
but,
I mean,
just
I think the thing that makes a lot of the tech audio stuff that I do resilient to criticism is because the games that we're working on are not perfect entities. They often have their own quirks and weirdness, and if a person corrects a thing, it's like, oh, thank God, I didn't know that's what solves this big problem or something. Yeah. Whereas I feel like if I was disappointed that someone corrected me, I'd be like, oh no, this is really hard. But sometimes people will try and correct you one way, and it's like some minor version has come along that's changed some virtualization behavior somewhere that you happen to be on, and you're like, oh, actually, it didn't work that way for us.
Yeah, and by correction, it's usually often not like you're not necessarily. Sometimes people are wrong, but sometimes it's like, actually, this is the reason why you guessed it was A, but it's actually B, and we didn't document it, or like, hey, that was a bug, or some explanation is often a thing.
I feel like the attenuation, what is it? The attenuation editor. If you ever make a video on the attenuation editor, you're usually wrong about something in that list of parameters.
Yeah, the attenuation settings track.
Jump off because it's white on white. Terrible idea.
You're
Uh-oh.
good.
Uh-oh.
All right.
Take it off. My God.
Wow.
It's happening again.
Hey, there it's happening again. I have this problem where I just take my clothes off on live streams, and
What
have
can I say? Friday morning, right? Oh, this is different. Oh, it's not. Oh, it's Eevee. Oh, this is different platform.
It's not OnlyFans or whatever. It is.
Yeah. It's we're on LinkedIn also, actually. So this is good for your resume.
Oh, baby.
Any
Is that what
future
LinkedIn's used for?
employers
Honestly, I
that's
can't
what
tell
they tell
these
me.
days.
Do we get a free PhD from this, or is that?
I always get confused between TikTok and LinkedIn. Frankly, I don't know the difference.
unaccredited. Yes.
Yeah.
Yeah. All right. Look what we got. We got a chat going. We got people who are impressed.
Whoa!
Look at that. Wow.
What's funny is there's a delay, like so you don't know exactly what that's responding to.
Yeah, that's kind of the best part.
I'm gonna guess it was one of my jokes and not you ripping your clothes off.
Yeah, it's probably not that.
This one was for the clothes, though. This was definitely for the
Yeah, that's fair.
That was all of our faces, actually.
Oh yeah, we got a lot of regulars, Steven and Angelites in here, and some new folks that I haven't seen. Thomas Scott and
We got some impatient viewers. We got somebody who's
someone's just like do an
audio. Come on, Dan.
Yeah, we've got. Well, I have audio lined up here.
Yeah.
So just a couple things for the people at home. There's some new stuff. Obviously, we've got David, and I've sort of switched to this window, like this automatic screen management thing. So I don't know how that's going to go. I can like set
add as many people
in focus, like so
nice.
you can be like, hey, there's Eric.
It's like the jumbotron,
and we can do one of these things, which is kind of interesting.
Very fancy.
The features.
I want to see how many people we can pack in and like how efficient the subscreens are. Like, can we get like 20 people all squared out? You know.
Well, so there is an upper limit based on my like how much I pay
your
for
budget,
this, basically.
So it's 4, isn't it? It's 4.
No. It's higher.
It's 4.
Totally.
We'll see how it goes. But yeah, so I have something to share. I don't know if anyone else has anything to share. Maybe no one else has anything.
Let's start with you, and then we will critique the shit out of it.
Okay.
Yeah, we'll just destroy
just
it.
2 hours of just
2 hours of brutal
scraping me across the pavement.
desiccation.
Yeah. Sounds good. Exciting. Okay.
At the very least, this live stream will humanize tech audio people that presumably are supposed to know shit, and then they'll realize we don't know what the hell we're doing.
Yeah,
that's the.
Turns out, game audio people are people too.
Yeah.
All right. So so this weekend. Okay. So basically, last week I received some new modular synth modules as one. Actually, let me just go back to the story.
You mean like in physical hardware?
Physical hardware.
You should show them your thing. You have your background blurred, and you tried to show us earlier today, and it did not work. So
Zoom's better at background blurring. Oh,
yeah, so we can't see that shit.
Ooh, what is that?
It's tantalizing, but to me it looks like blurred out.
This is like a 90s 90s Aphex Twin video.
Yeah, honestly, you're teasing me, Dan. I gotta see what you're showing me.
Anyway, yeah, it's basically Steam Synth is the manufacturer, and they have some. I think
do you have a link to maybe so we can look at it online?
That's the other thing. Oh, David, I forgot to mention. So there's a on the chat section, there's, if you see on the bottom, there's a private chat. If you can send me a link, I'll add a link to your YouTube and/or website or whatever.
Yeah, come on, we gotta
to
let
the
David
video description. Yeah. If
like
anyone
and subscribe to David Weaver Audio. Like
yes, yeah. Sorry, that is the YouTube form.
hit the
right?
notification button on YouTube. Be the first to
subscribe first. David's got a pretty good following, I think. You know,
I know.
It's but he could have more. That could be you.
I'm going for 4 or 5 mil. I reckon that's got to be.
That'd be great.
Tech
That'd
audio.
be great. That's right.
Yeah. What's the tech audio audience? How many people do you think there are in the world who's interested
in
in
the
tech
world in tech audio?
world.
I don't know.
We're talking maybe 10 billion people.
Yeah.
Yes.
Good estimate.
This is like that argument, you know, when you get pitched a game and then they're like, oh, you know, but Fortnite has like 3 billion players. So, you know, if we just got a small fraction of that, then we would have like 300 million players. And you're like, yeah, that's not going to happen.
No.
You can actually check the Fortnite players at fortnite.gg /player count. They are public numbers. And I always find that really interesting just because, I don't know, it's fun to see tickers. But anyway, so I saw.
It's kind of what we get into this for, right?
Yeah, I love just watching
Fortnite players. GG.
Partly, I also am into this. So yeah, I bought some modular synths. What of it? No, it's this is how I.
What's the name of it? The thing I'm gonna Google it because you never linked it.
Oh, it's Fortnite GG /
No. His synthesizer.
So the company's called Synthetic Sound Labs, but their website's called steamsynth.com. And I collect the Moog unit size, which are called 5U, which is sort of large format. And they have a bunch of a bunch of modules. But I recently got a couple of Thru-Zero FM oscillators. And the idea is that, and you can look it up, but basically Thru-Zero allows the modulation to go into like negative values. Sort of, it flips
negative what values?
Negative values. So you have like a negative modulator signal. It just flips the output, and so the result is typically a more musical signal as a consequence of that. And there's a bunch of like YouTube videos you can look at, talk about comparing regular and Thru-Zero. Anyway, that was the inspiration.
This is your thick boy cable modulator, right?
Yes.
What's that called?
It's called Moog unit.
Okay,
or 5U because it is literally.
I think of it as the big cables.
5 rack units high, whereas 0 rack is 3 rack units high.
Got it.
So
yours is bigger. That's what
it's big. Yeah. Well, you know, so here's the thing: is the reason I got into it, aside from I thought that it was cool, is I felt like I could achieve a synth wall faster.
That's true. Less modules, bigger
more space. I always thought it because you were a hipster purist. You know, like your tiny little synthesizers.
That was part of it. I won't go into the story too far, but I had the privilege of visiting remote control studios.
Yeah.
And
bragging.
that's what he had on his wall, and
that is a wall too.
And here's the thing: is what's not obvious is there isn't secret sauce. There's always this sort of paranoia especially when you're a freelancer, that there's some sort of special sauce that the professionals have that you don't. The special sauce that they have is just money. That's it. That's all the special sauce that they have. And so, when I visited, RC, it was like they were on Pro Tools and Cubase. It was just everything you've already seen before, right? Just more resources pushed at it. And but what I didn't have was modular synths. So when I got into it, which is a terrible idea, never once, as they say, modular synths, because you won't recover. And yeah, I got into 5U anyway. So I have found getting older, I appreciate the larger knobs, the larger text. I do have some Eurorack stuff, and I'm like this, like, getting real close. I gotta get the light up on it,
the tiny thing. Honestly, that's the tiny
It
knobs.
is.
I went even the opposite. I've got all those 1U like tiny
Oh
slices.
yeah, I can't.
Because I was
see those
like,
at all.
I have a whole shit ton of those, and I'm like, oh man, I can fit more in my rack. And then I'm like, wait a second,
No.
like,
I need like those
not
old
to be cool.
reader like magnifying glasses for that.
Yeah.
Yeah,
yeah, exactly.
Still some Moog tweezers or something. There's
Totally.
an opportunity there.
So this is my synth rack on this side.
Yeah.
You can see it, and I at the top row is unfilled. So I like
So you've
my
got all that
modular
room.
synth quest. I have almost a whole row that I still need to fill, and
What's
I
the
look
width?
at it.
What's the width? How many HP?
It's I'd have to calculate it,
Yeah.
but at least $5,000 worth of.
That's
Yeah.
about as clear a metric as any.
Yeah, exactly. Anyway, so you got this
Yeah,
thing,
anyway,
and then you're
yeah,
like,
so-
hey, I want to build this in software because I'm
Well,
crazy.
so I've been, as people know, I've been kind of getting more into making custom meta sounds.
Yeah, Dan has
Meta sound
been
notes.
driving everybody nuts, making new nodes and checking them in and shit. So
Yeah, it's been fun. Well, and I do the crazy stuff at home, and I don't bring it to work, so don't worry about it.
he brings the good shit. He comes in, he's like,
I
hey,
do
guys,
bring some of the good
I've
shit.
been
that
smoking
low
this
end
shit, I'm
thing.
taking it in.
Good.
Yeah.
So I will advertise that he's been checking a bunch of shit in. So if you have our GitHub, you can see our experimental Metasound plugin that we have. It's available, and Dan is going through the code reviews. We're reviewing it, giving him some feedback, and he's getting it checked in. So some of the stuff is actually making it into the experimental module. Whether or not we get it promoted to the non-experimental space.
Well,
I'm actually tomorrow.
mine's-
I'm going to pin up our official internal policy because Dan's kind of forcing the issue. It's like, okay, how do
Yes.
we? What's the actual process to get experimental stuff released non-experimentally for in terms of new nodes?
I actually snuck one into the standard set, so
I know. That's made me go.
I got my
There's
sub-harmonizer
there's a
in
new
there.
policy.
Yeah.
So
It's
Yeah.
a problem because as soon as it goes into the non-experimental space, this is a real interesting issue. That means some random sound designer in Fortnite's going to go working on Fortnite is going to say, "Oh, what's this sub-harmonizer? I can use that, right?" And
Yes.
then
The answer is yes.
It's me.
and then like suddenly Fortnite's using it, and they're like, "What is causing this?" So we gotta figure out a more sane process here.
I'm the one that's going to use it too. So
Yes.
Yeah, so there
It's
needs
fair
to be some guardrails up there, trying to balance it. But anyways, I'm all for encouraging experimentation because that's the whole idea of Metasounds.
sounds like you hate it. I don't know. You just anti.
I do kind of hate it too, but no, for real. I'm excited when Dan's like, "Hey, I was experimenting with shit." It's always like, "Oh, that's creative and interesting." For my And I also go like, I wish I had time again, in my free time. This is it. This
You're
is my
jealous.
free time for the week. Is this
I
call?
see. Yeah, yeah.
Frankly.
I
Like-
appreciate it. I think everyone at home appreciates it as well. Yeah. Wouldn't
when
be
it
the
comes
same
to, like,
without you.
getting a new module or something, Dan, is your first move to make it like a meta sound? Is that something you find yourself doing a lot now in terms of just, wow, how does this work? Or like, what's the invention
Good question.
idea behind why you want to do that?
Yeah, that's a good question. But so my I go into the Metasound space when it's going to be procedural audio related. So that because for two reasons. Number one, despite all of the boilerplate that's sort of required for the Metasound to sort of stand up Metasound code, the Metasound framework, just like the rest of Unreal's sort of audio framework, is actually a really good space to experiment with DSP stuff. So if you're going to do something with like DSP,
Yeah, it's good for learning.
There's already like a strong framework around it, and so it's really easy to sort of like focus on like just the audio generation, like the callback block, and and so you don't have to think about and there's already a bunch of stuff already for like, how do you get the data from the
Yeah.
thing to the thing? That sort of stuff is already
Yeah,
kind
well,
of built in.
a good thing that we recommend, and Dan does this, is like find a node that's kind of doing something similar to what you're interested in. The code's all there. Go grab the code, dig through, and go like, oh, how did they do the thing here? That's how bad stuff propagates.
That's true. Yes.
But it's also how like you learn. So so it's not a bad thing. Grab if you know C++ and you want to know how something works, just grab it and then make your own. And then once you've done it a couple times, it gets fast. The boilerplate gets easier to deal with.
Yeah.
Yeah,
it does. But that's something that also is incrementally improved over time.
Yeah.
Like I think that even just making a meta sound now is better than it was, a few
it's about
years
to get a
ago.
lot more complicated with node config. And
I know. But node configuration is interesting on its own as well, so it's fun space to explore. So that's part of the reason. I think the other part of the reason is the environment for auditioning and sort of seeing seeing the results of it. Does this work?
it's a fun environment to mess around in.
Yeah. So
Often, not always. When it's not working, it can be frustrating. But but like the average case might be fun. I don't know. I can say that.
But it kind of makes sense. Like, I think a lot of people get into DSP through like the juice and plugin sort of route, and that's good, except that you do handle more of the architecture yourself, which can be a little bit challenging. So Metasound having that sort of safe space to play in, and then just having, I want this much control makes more sense than let's reinvent the wheel or build it all out. And it's similar to the PD Max sort of small DSP fragment sort of approach.
And the ultimate thing, this is, in my opinion, the real killer aspect, which is counterintuitive to audio people, is the context that it's in. In other words, it's in the Unreal Engine, and you have all the rest of the Unreal Engine at your disposal to get the data to and from your meta sounds. So it's actually, ironically, the graphics engine and the animation and VFX tools and all in the sequencer and all that stuff that really make meta sounds really unique. So it's like the not audio part is one of the things that makes it unique for audio, which is counterintuitive, but it's totally true. It's a major advantage because to do a lot of the stuff that's trivial in UE is like really hard to stand up in Maximus P or Juice or whatever. You can go, I'm going to do my little tiny little audio thing that's my unique contribution, and then I have this freaking massive particle system that I can do crazy stuff with, so that's one of the other unique advantages, I would just say, or home field advantages
for when it, especially so when it exactly, it's like you've got a DSP graph that comes with a free game engine.
Exactly.
Right, but also sometimes the game audio is also the context of my experimentation, right? So it makes sense to sort of audition in that space.
Show us your
graph. So here's my hold on, let me bring this over where it's more visible. The screen, sorry.
If you do check this in, you cannot call it Thru-Zero.
I'm not. Don't worry about it. I'm not checking it in. It could be some. I don't even think this is exactly what someone would want. This is just what like I said, this was an experimentation of mine. Actually, does this work? No, I can't. Can I do this? No, it doesn't do that. Okay. Sorry, there are limits.
You want to have your face below it and have it be the.
I thought it would be fun if other people, if they could see you at home as well. But I guess But as long as they can hear you, I think that's fine. There's just limits to this way of this like this dynamic scene thing, whatever it's called. Anyway, so I have a quick little example. But here's two of the oscillators. The naming thing is just one of those things. It's hard because I named it before I knew it worked, right? Because I set the code down first and gave it a name, and then I tried to make it work. So I don't even know. This is the thing I'm going to bring up here is I don't even know if I did actually do FM or if it was just phase modulation in disguise. So this is something maybe Aaron can comment on.
Well, I can answer. What's the difference between frequency modulation and phase modulation? Anybody know?
As far as I can tell,
not a trick question.
As far as I can tell, I mean, unless you want me to not answer.
No, answer it. Or,
Well, as far
or
as I
Eric.
can tell-
Eric. What? Eric.
Oh,
Eric,
Jesus.
yeah, that's right, Eric.
Eric.
Quiet.
What is the difference?
One modulates phase and one modulates frequency.
Yeah, it's not a trick question. That's literally what it is.
Pretty good answer.
I mean,
Close one.
that's it. But why would one do one versus the other? Phase modulation is easier because the phase is, I would say, more linear and consistent when you modulate it, versus frequency, which the frequency of an oscillator is exponential, and so the math is, I think, a little bit more complicated to get a controlled frequency modulation, and it's more expensive. Phase modulation is simpler to understand, easier to implement digitally, and more computationally efficient, which is why Yamaha DX7s, the first FM synthesizer, was actually phase modulation.
Yeah, digital FM synthesizer.
Yeah, the first digital FM synthesizer. Yeah.
Yeah, and I will also note that I did no optimization here, so it's probably pretty terrible.
But before you, I mean, play your demo. But I think for the audience, it might be worthwhile to talk about audio rate versus control rate modulation.
Yeah,
as
I
a
think this is a
concept.
good idea.
Yeah. All right, do your demo.
Yeah. So do my demo. Okay. So yeah.
Do it,
Well,
Dan.
first of all, I just want to sort of.
What's your toy, Dan?
I just want to. I have I have two demos here, real quick. I have one where I'm going to show, so you just sort of hear what FM does,
Yeah.
what the modulation does, and then I'll sort of, I have a composition that I made, which I sort of shared earlier today on my YouTube, that actually uses it as like in a musical context. But yeah, so here's, oops, here we go. Here's my oscillator. I've got it quiet here. I don't know. Can this?
By the way,
is
I
this
love
audible?
that you're using the sonogram.
So nice.
Yeah, I threw all of the things on there. I was like, let's do it all. Is that audible? Is it good? You've been sharing it?
Yep.
Painfully
Yep.
audible.
Is it too loud?
Little bit. It's also sine
Is that better?
Sine wave.
I love this
Yeah.
song.
This is a good frequency. But yeah, anyway, so so basically it's frequency modulation. It's modulating the frequency of the signal, but it's usually at audio rate. Now I'm going to do it at sub audio rate, so you can kind of hear what that does. So this sort of get a wobble. The pitch goes up and down. But what happens is when the modulating signal gets into audio rate, which is a audible range, a hearing range above 20 hertz, the signal gets really interesting. It starts to create sort of like an interesting timbre. So let's go up. And this is two sine tones, and you can see on the sonogram that a bunch of interesting sidebands are being created as a result of this modulation. And
The sidebands are the characteristic sound of that.
yeah, and the more that I add to the signal, the amplitude, the significance of the intensity of the modulation, the more interesting the characteristic can get. I mean, you can get really crazy, like.
One interesting to listen to this. I saw someone complaining in Discord recently about this. You get this kind of stair stepping when you control the knob.
Mhm.
One of the things that people aren't quite grokking that I can see in the community is like in the UI of the Unreal Engine editor, there's like a UI update rate, and it is very slow relative to even the block rate of the Metasound graph, which is like 100 FPS. And so it's really an artifact of the UI and the knob of the UI. If you were to hook that up to an LFO, it would be continuous. You wouldn't hear this the stair stepping.
Yeah.
Even at block rate, it would sound better.
If you want, sometimes this can help. Is this interp to which I think is one of your nodes, Aaron?
I wrote a lot of notes.
This will.
We had a bounty board during the height of 5.0 launch, where we just had a list of a bunch of nodes, and it was like whoever can get to them, and we're just like, there was like 2 or 3 weeks where we went from like one node, it was like a sine tone, to I don't know how many, but like 40 nodes before 5.0 preview.
Yeah.
It was like a fever dream. I don't remember what it was.
so what's interesting about this is that we actually have two sine tones, which normally have very simple timbre, right?
Yeah.
They're pure tones, they're pure frequencies. And then this interrelationship, this modulation, creates complex timbres as a result. And so that's and then I also implemented a feedback. It's like offset by one sample because reasons. And so this is basically it is modulating itself.
That's crazy.
Which is kind of interesting. And so then you can get really interesting results sort of with a combination of these.
Notice it's smoother now, by the way, when he did it.
Yeah, because I added these functions.
By the way, we've thought about in the editor automatically doing knob parameter interpolation.
Sometimes you want to
as a feature because this is such a problem because people bitch about the like stair stepping on the UI. I just want to say, let us know if you like that.
Another thing is I also implemented a nonlinear transformation, which is basically exponential. So now the signal is transformed to modulate logarithmically, and so the as a result there's a sort of softening to the effect because more of the modulating signal is in the lower frequency range. Okay, so that is a sort of gist of how it works, and then here is
wait. Can you go back? I want to. I wish I could play it myself. Can you put up do the feedback and the mod indexing? I want to hear it.
Sure. So we can do like this. And then we can add. And then we can do this.
Yes, that's what I'm looking for. Look at that sonic.
Oh, that's cool.
That's nice. All right, you got to check this in. Dude,
that's cool.
So it's very fun to play with. It like Aaron mentioned the DX7, but also like so many sound effects from the 80s and early 90s are influenced by FM synthesis. And so you'll hear stuff like, from your favorite anime or whatever. We use a ton of FM synthesis. So it's a really fun playground. And so anyway, so that's and as
wait, I have one more question. What is the linear?
That's what I just switched. So here's if I switch back.
Oh, I see. That makes everything.
Basically, it's a linear or exponential mapping of the frequency range.
Got it. Okay.
Yeah.
Cool.
So so here's a musical composition that I sort of did. I woke up really early in the morning, and so what do? You play around.
I'm literally imagining you as a zombie at 3 a.m. By the way, in your like robe.
Correct.
Drinking. Do you drink coffee? So you're drinking your tea.
Not at 3 a.m. That's when I want to go back
in the
to
dark. So think of Dan in the dark in his bathrobe making this piece of composition.
Yeah.
So all these sounds are the FM synth?
Yes. Yeah, all sounds are the FM synth. And I'll go through them a little bit. But it's procedural. I've got every 8 bars, it'll update the seed. And then I have 3 instruments basically playing.
This is a menu selection screen.
Yeah.
For your hipster 90s throwback.
Yeah.
It feels like Ace Combat. Ready for it.
Nice. So let me isolate them a little bit here. I didn't really set this up for isolation properly. So I'm just going to do a really cheap one here. But so here's the first instrument here. And this is actually a patch that I made. And FM we'll call them algorithms, are set up of operators in particular series or parallels. So if you look at if you like look up patches for FM synths, you'll actually see the algorithm will be a diagram of squares feeding into other squares, feeding out. And if we look at this particular patch here, let me actually quit this one here real quick here. So this is two operators. So basically FM, we call them operators. Excuse me. We have two operators in parallel, getting mixed together, and then modulating this last operator, which goes out. So this is the only one that you actually hear, and then these two are actually modulating this one.
Yep.
And they have two different roles. But the job is one of them is doing like a tap sound. That's sort of part of the attack, and then one of them is doing kind of like a growl sound. And so if I isolate them here, you can kind of hear. Well, actually, let's do none of them. So you hear just this.
Well, one of the interesting things here, I just want to point out, is because we didn't talk about it, even though I said I wanted to talk about it, which is this idea of using an audio buffer to modulate. Mm-hmm. So we didn't talk about that and why we want to do that. But like a second order thing I want to point out is that you are using a mono mixer to mix together modulation control data.
Yes, that's correct. Ooh. Yeah.
Which is a subtle thing that maybe a lot of people are picking up and is a cool idea. So you are mixing together a modulation signal, which is an audio rate modulation. This is really important. Why, Dan, Eric, why would you want to do an audio rate? And what do I even mean by audio rate versus block rate or control rate, first of all? And then two, why would you want audio rate modulation in this application? Eric.
Yeah, so your block rate's only going to happen once every 100 times per second.
By default, but it's the
by default
block rate. Yeah.
And so when you're at audio rate, you get sample rate, and so all of your math is going to be sample accurate, and it's going to be smoother, and you're not going to have the stair stepping that Dan kind of demoed earlier.
But there's even a deeper reason when it comes to FM synthesis.
Well, I'm not an FM synthesis person, but
so y'all are familiar with aliasing?
Yes.
This issue of aliasing. So aliasing is a deep concept. It's not just an audio thing, but the block rate defines the maximum frequency, essentially, or whatever your sample rate is. The rate at which you are deriving input on a parameter defines the maximum frequency that you can accurately represent before it starts aliasing. So if you're doing 100, block rate updates a second, what is the maximum frequency you can accurately represent? Dan. Yep. Yeah, I used to be a teacher, by the way, so I'm like calling the class.
So did I. So did I. And Nyquist was one of my queries.
So what's the Nyquist frequency
it's 50
of 100?
hertz.
If your sample rate is 100, what's your Nyquist frequency?
50 hertz.
50. So that means the highest signal that you can represent at 100 blocks per second is 50. Yes. 50 is not a very high
rate. It's important to sort of acknowledge that 50 hertz, even at the edge of Nyquist, it's pretty crude. You can only the resolution is really
and getting shitty the closer you get up to 50. So in other words, the highest frequency that you can quote modulate something and still it being accurate and not alias is 50.
Yeah.
But frequency modulation, you're modulating that shit you're modulating at 800,000 modulations a second, which means block rate ain't gonna cut it. So you have to go to audio rate so that your Nyquist frequency is 24,000 oscillations a second, right?
Yep.
So that's the real reason why you need to go to audio rate, and there's no way around it. If you want to do FM synthesis in a language, or not a language, in an environment like Metasounds, you have to jump from control rate parameters to audio rate parameters, which then have an implication that your audio buffers that are in that modulation are things that you do not want to listen to. This is a dangerous thing that you're doing. So don't take that audio rate control value and stick it to your output. You could blow your speakers up,
Actually, I do a transformation.
We don't yet have nice control hard.
Well, hold on a second. I actually do. So no. Hold on. I actually do a transformation. So my input range is -1 to 1.
Yeah,
so a
because you're doing
normal audio
phase
signal
modulation. Yeah,
will work. So
that's
it's
another reason why phase modulation is better for digital because of this issue.
yeah.
Because phase modulation is negative 1 to 1. Frequency modulation, or OG sinusoids, you have to modulate it with enormous data, and don't listen to that. But yeah, on phase modulation is one of the reasons why it's better.
Well, I'm actually doing the transformation in. This is why it's not optimized, but I'm doing a transformation to frequency domain or frequency range.
Oh, yeah.
And so that's yeah.
We have to look at the code and I'll critique
But
it.
I have to do
theory than it.
Yeah, I feel like I have to do that because the frequency modulation is the frequency. It's additive anyway. So we can look at the code. We'll look at the code, but yeah. Anyway, so
but even with your unoptimal code, your massive FM synth was only taking 3% of your CPU, which
it's not bad.
Which is kind of heavy for a video,
it's a little heavy,
but it's not bad if you.
I'm sure there could be an optimization pass.
Yeah, exactly.
Sure. But here's the other thing, and this is actually an interesting point that I would like to make, is that because of that degradation of sample quality as you sort of approach Nyquist, I actually constrain. And this is actually a tip that I got from one of my books. This is called BasicSynth.
Dude, when are you gonna learn that your background blur?
No, that's what it looks like. That's the book. It's really hard to read, honestly.
The whole book is blurry.
Here we go. It thinks it's part of my face.
The zoom algo is like, this guy's face is fucked up.
The person who wrote this is kind of crazy, but I feel like is pretty well explains the stuff. Anyway, one of the recommendations they make is like limiting the like modulation max frequency range because of this. And so I actually thought about, I didn't want to do oversampling.
Yeah.
So yeah. So
all right. I took you way off of your vibe, but I thought like a technical explanation on this would help.
Yeah.
If you want to get back into your thing.
No, look, people are digging it. Look at this. Clara is, hey Claire. Clara is like, that's a great explanation.
I don't know exactly what she was referring to. It might have been your zoom blur out thing. I don't know.
All explanations are great. Okay.
She meant, by the way, if you ain't redlining, you ain't headlining. She corrected.
That's right.
I thought it was a resolution pun.
I know. At first I was like, what? Which I've never heard that before. That's actually really cool. That's a cool saying. I don't wonder if she made that herself up. It's got to be a saying.
It's a Clara original. Anyway, so here we have two operators getting mixed together. Now you know why. And going into modulating this one operator. This is the only one that you actually hear. And so if I just play this one, I have an envelope on this and stereo control, but just an envelope on this. And if I just have no modulation signal, it's as you would expect. It's just a simple sine tone. If I add the tap to it, you can hear.
Love that sound. Such a great sound.
And as it gets more intense, and this is one of the things that I like about FM synthesis here in this context, is you get a timbral shift. So it kind of has the kind of response that you would expect from like a membranophone.
Yep.
Totally.
Where you're like physically modeling some kind of drum head.
Yeah, I mean it sounds synthy, but it's the kind of approach that you might take to.
Can you scroll up a bit? So where's your envelope? Your AD envelope is the thing that's making it short. If you were to make that decay time, let's say like 0.6,
yeah,
that would be like boom, right? Yeah,
it'd be longer.
Yeah.
I could do like 2 seconds, and I don't know.
Yeah, just to make it clear that envelope is lifting a lot of weight there.
And you could tune it, yeah, if you want like a really tight.
Yeah.
tight
nice
attack there.
bass drum sound.
Yeah, exactly. Yeah. There's this. All of these parameters. If you were getting into like instrument building, all these parameters could be parameterized. Added as inputs, and then you could have a lot of flexibility in terms of your
with node config. We could redo that AD envelope. You could select it here. Select it. Select the AD envelope. I just want to bring up this idea of node configs. Just select the node. And then the lower left down there, visualizing what the envelope looks like, being able to draw it.
But we also have the
on graph drawing.
On graph,
Anyway, so there's things that we can make this even cooler.
Yeah.
The sound has that very like mallet physical modeling element to it too.
Yeah. Yep. Yeah. Well, so one of the differences between this and say ring modulation is that a lot of the timbre is still very musical, right? Where ring modulation will be sort of like non-harmonic relationships between the output.
It's really hard to control ring mod.
Right, but that's one of the things the ring mod can be really good for making metallic sounds. Yeah. Because you get these sort of non-harmonic relationships between the resonances. Anyway, bringing this back. And then this was to control the growl. So you get like that. And so this is also envelope based, but it's just like half second up, half second down. And then I have like because it's linear response. So I have like this, I'm really shrinking the signal a lot here to keep the range real low.
What happens if you boost that up? What's the sonic effect?
Like it gets a little more, so if I do if I go like say
that right there is just kind of a mapping function. You could have gotten rid of that and made your OPB go to a mapping function. I get what you're saying.
Yeah, it's just a simple scaling. Yeah.
So really, that OPB is going from 0 to 0.05, not 0 to 1.
Yes. Yeah, but this is but one of the things that I like to do is make my inputs normalized.
Yeah.
So that the user can expect a full range.
Yeah, it makes sense.
Yeah.
For good sound. So part of this is the sound design. Like this is instrument design. This is sound design. And so part of me is thinking about, what are the sort of ranges that still make sense for this sound.
Yeah, what I'm saying though is you could have been a little bit less obscure that what you're doing here. If you draw off OPB, like just drag off of OPB, your pin.
This one?
No, the output of your knob.
Oh, whoops! Fucking hell!
I don't know what you did. I'm probably gonna break it. Anyway, so drag out type map range.
Oh yeah, I could have done that.
So float. Yeah. You could have typed 0 to 1 and then done 0 to 0.05.
Yeah,
and it would have been the same. Take up more real estate.
Would have been the same. Yeah.
Yeah. All I'm saying is that what you're doing is essentially the same thing.
Yeah. That's a good point. Yeah, this is basically just mapping the ranges. So that's the idea with this. And then let me these were set at 1. And so if we go back in, here's my my first instrument here. And it's just got a procedural rhythm using the trigger filter. And I was playing around with some tones, and I just liked it as like a pedal tone. So I just gave it a single C note for that. And then I have random values getting passed into the sort of operator A, which was affecting the tap intensity. And so you get some variation there. And then I have an LFO that's just constantly sort of bringing in and out that sort of growl sound.
Yeah, it's great. That like
and then I have the same thing, but all I did was I just panned the sound and just sort of set the values right off the bat, and that's giving the sort of
the stereo delay is
stereo delay is doing a lot of cool work here.
The ultimate.
But I've also got an LFO going into the pan, so it's swirling around the stereo delay, and so you get ping pong on top of that, and then it's going through reverb because why not?
But I love that somebody added a reverb. That's not from Harmonix. I can't remember who did that. I was kind of opposed to having.
Yeah, I don't remember who.
The graph. I think they did it for Patchwork. They couldn't do dynamic sub-extends or some shit for some reason.
Yeah. And then I have an LFO controlling the volume of this whole instrument. And then I put together a simple little bass sound. I wanted something that sort of was a little bit different, and this one's kind of interesting because what happens is it rarely plays, so it's got a 20% chance of playing, but the pitch is updated all the time, and so when it does play, it plays longer than one update to its pitch, one trigger update, and so there's a pitch change mid note essentially, and then I've got an envelope controlling the feedback, which gives it a sort of a bend, a sort of pitch bend to it, and so it's got this sort of. Let's see if I can. Said it was rare. Just got a bad roll there. Let's see if it comes in now. This one. There we go. It updates every 8 bars, so the seed changes, and so you get new rhythms every 8 bars. Yeah. Anyway, so that's the demo part. Are there any questions before I? How are we doing on time? Actually, we're doing fine. Are there any questions, concerns, comments, queries?
It's really cool. Sounds awesome.
Thank you.
I like it, Dan.
Yay! Validation.
I want to play with it. You know, I have had an ambition, but I haven't. But maybe with your node, we can get it coded, we can get it in, and we can try it out. But you know, if you is this something we could talk about? But DX7. I have a DX7. It's like my first synthesizer, actually. I have it in my closet. But one of the things that they have is this really cool PM, so phase modulation, like chart on top of it.
Yeah, the different algorithms.
Yeah, the different algorithms, and I had this idea of trying to emulate that and come up with like a meta sound flavor of it, and I'm trying to hunt it down. But it's so cool, and so with your thing, maybe we can do that. I'm looking for this algorithm chart.
Yeah, there are a bunch of canonical algorithms. It can get pretty crazy because like the 7 is aptly named. It has 7 operators.
Yeah.
I have like one of my fun synthesizers. I don't get a lot of digital synthesizers, but one of the fun ones that I have is the
here we go.
The Sega Mega Drive sort of synthesizer, and which is all FM. And so, what are you showing something? I don't know if you're showing something.
I mean, I can. I did find a website that just goes deep into it.
Yeah. If you want, I could send me the link and I can add it to the thing.
Yeah, I'll send you.
Is it in Operator in Ableton where you can kind of flick through the presets and it has all of the different graph combinations of X amount of operators?
Maybe. I don't know. I haven't. Aaron's a live user.
Yes. It's the same kind of idea.
Yeah. So those are usually, those topologies tend to be, especially on hardware, are like sort of fixed, and you sort of like can switch between different preset flavors, basically.
But with Metasound Builder.
Here is.
Yeah.
Yeah.
So this website I found, somebody's 2019, I guess, but this DX7, you can kind of see what a DX7 looks like if you haven't seen it.
Yeah.
Oh, great. But anyways, it's this really cool thing, and on the top here you see all these algorithms. It's a terrible picture, but he goes through it here.
Yeah.
And this is what the top view is.
Can
And
can
here's
you?
a
Oh
zoomed
yeah,
in
there we go.
one.
Yeah, there we go. That was
Uh,
not a zoom.
There you go. So there we go. And you can see here, there's like a whole ton of these algorithms, and he's kind of explaining through here how it works. But these are all the same essential. You can see right here this feedback. Dan
Yep.
implemented a feedback. So something like what Dan made could be done, could be used to implement all of these algorithms, like a really
Yeah.
simple phase modulation, basically unit constructed in this topology with certain parametric exposures and can create all of these crazy cool sounds.
Yeah.
And it's in my opinion one of the coolest digital audio things that you can create such a wide variety of sounds.
Can you
and
pick
transform them.
one of them real quick? So I just want to sort of go through. Yeah. Can you maybe go
What do you
back
mean
to that
pick
one?
which one?
I don't know. Pick a picture to blow up one of these diagrams. Okay. Yeah.
Yeah.
Oh, that's good.
Or zoom into
Well,
it or
even
whatever.
smaller.
Okay.
Yeah.
So you see number 1 on the left there.
Yeah.
So operator 1 and 3 are the only ones you actually hear. Operator 2 is modulating 1, and then you can see that it's 6 is modulating 5, 5 is modulating 4, 4 is modulating 3. And so you can imagine, I just in both of my scenarios, both those things that I set up here, I only had one level deep in terms of modulation.
Yes.
But you could imagine that a modulated signal feeding into an. I mean, we don't have to imagine. We can put it together right here. But I'm just saying, like, the complexity of the waveform gets increasingly so, and so that you can get really interesting results from these more complex sort of systems.
Yeah, this kind of explains it. You know, you can see that between the towers, there's no modulation; they're added. So these are kind of like mixed output.
Yeah.
But anyways, it's pretty fun. The DX7 has this horrible cheesy sound, but anyways,
It sounds great.
Anyways,
just watch Law and Order, and you'll hear the DX7.
Yeah. Dong 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 dong. Anyways, you can stop sharing my screen now.
Yeah. Right. Cool. Should we look at some of Dan's code?
I like it.
All right.
You're brave, Dan.
This is why I do this.
I started on my second beer, so
All right. I'm expecting the
So we're ready for
best
code
review.
review.
That's right.
All right, so I got 16 notes so far, and I'd like to go through them.
I mean, this might explain, our code review process. But in you have to be 2 beers in to start looking at code.
Okay, so let's we can do the sort of the boilerplate here. We've got. Hold on, let me do a little zoom in here for folks.
Can you close your output too? Your log on the bottom?
yeah.
He was trying to optimize your.
I don't want to close it. Well, I'll do this.
There we go.
You can always reset your layout.
I don't want to have to do that. Anyway, so here's
You do you, Dan.
So here's the vertex names, right? So this is where we declare the names for our vertices, including the names and the tooltips, inputs and outputs. We'll skip this right now. This is my processor. Then we have our operator declaration and all of our usual suspects: the get node info, the get default interface, these static functions that can be called on the type to get, in the case of the information about this type, so that it shows up on stuff and is available, and without having to actually make it. And then the get default interface gives us the default interface. We just build it here. And then the last static function, which is create operator, where we actually create our read refs and stuff them into the constructor here. So this is just the inputs. Boom, go right into there, and then we have our constructor. Super simple. This is a. I think previously we looked at Metasound nodes where it was just like just doing some math. In this case, we're actually doing some DSP, and so I need to get the sample rate and the block rate. And so that's data that I get. And then I also initialize my processor, which is up here, but we'll get into that a little bit later.
Hey Dan, there's some questions.
Oh yeah, sorry.
You're diving in as if like this is the end of the semester. We might got some noobs here. So can you scroll up to the top at the very top?
Hold on. Yeah. Oh yes. Sorry. Yep.
By the way, I don't know how to type to people listening on this.
You can't unless you go actually to the stream.
Oh, I have
but
to go to
if you see something and you want to like shout out a question, that definitely.
Cool. Right. So Dan has a lot of includes. Probably many of these he doesn't need.
This one I don't need. I have resharper, and resharper's analysis says there are like 6
all the grayed out
ones. Yeah, these ones don't need that.
So, but somebody's like, why do you have so many includes? We actually do try to break down as much of our stuff into separate files. It actually helps it because otherwise you have like one gigantic monolithic include.
Yeah.
Which slows everything down. So we actually do like to break it down. So that means that though, unfortunately, got to have a lot of tiny includes.
Yep.
The strategy is include what you use is what we call it.
Yeah.
At Unreal, it used to be you just do like one include and includes the whole engine or whatever. That sucks. So, anyways, so in a way, it is a little bit of a pain because you're trying to figure out what to include. Going back to what Dan and I said earlier today, if you missed it, go look at a node that's doing something similar, and one of the reasons is it kind of gives you an idea of what includes that you might need.
Yeah,
so you're like, oh, I see. If I want to do this, I need to include this name.
Yeah,
so that helps. Obviously, you don't have time to go to the rest of this, but there's a lot of shit here that you don't really need to worry about. But there's localization you have to worry about. Unreal Engine has this whole localization system, so you see this like loc text thing. Yeah. Just follow along of other nodes and type it in and don't think about it too much. But you probably won't need to worry about it if you're out in your own space. But for Unreal Engine, everything that we check in like gets localized to 30 languages or whatever, how many. Yeah. And so there's like a magic system that registers all of the names into this global file, and it goes off to an army of localizers, and that's how Unreal Engine works in French.
Yeah, and in fact, if you look at there's still remnants of those macros in the get node info, sort of typical get node info. You'll see the sort of loc text is sort of like an implementation of the text loc text, macro, and you can see this is like basically this is the like key, and this is going to be the value, and then if this gets localized, then this will get swapped out.
Some sad person that has to translate Thru-Zero FM, and they're like, what the hell does this even mean? And they'll make a guess, and they'll never ask us, and they'll just go for it.
Correct.
That's the process.
Yes.
But if they don't know it, they probably just keep it the same, like whatever.
But I want to, but just in terms of localization, I just want to sort of state the text type. Okay, the type, so there's like f name and there's f string, but the text type, the f text type, is there for something that is meant to be localized. That's why text exists in Unreal. Right. And so if you're making a game and you intend it localization, any sort of text that you want localized has to be in the text format for it to be included automatically in the localization.
He's specifically saying that object f text. Line
and or in blueprints, it's just called text and it's pink colored.
And it has the flag icon next to it, which you probably have seen for localization.
Yeah. Anyways, there's the larger point is don't be intimidated by that crap. There's a ton of that kind of thing in here.
Yeah.
And sort of just crib along and don't get too anxious if you want to make your own Metasound node. Just go for it.
That's where I would say like look at a couple of Metasound nodes. Some of the simpler ones are good to learn from because you'll see the patterns. You'll see both these have this function, and then if you look at that, you can see the difference in what they're doing, and it will help you sort of. Yeah.
One interesting subtle thing, which I think a lot of people don't know why we're doing this, but like you see these macros, Metasound param and Metasound get param name and metadata. So one of the reasons why we did this, I made these macros, by the way. So Control G into it. I don't know. I think Control G should work.
I can just F12 into it.
Yeah. So I made all of these. Part of the problem is our Metasound boilerplate, the way we were doing it in the original days before 5.0 preview is. You'd have to. We were like hand typing all of the things as strings all the way down, and we would get typos and all that. So these macros are actually there to prevent typos for the Metasound stuff. It's not actually to make things shorter. It's to make it so that you avoid typos. So it becomes a compile error if you mistype something versus a string, which could compile just fine. And then at runtime, you'd be like, why is this parameter all messed up? And you're trying to test your node. So a little bit of a backstory on why these macros exist. It's to prevent typos, essentially. So the idea is go back to the CPP file. So at the very top, you'd kind of declare all of your parameters at the top of this file.
Yeah.
So like input frequency. So up here, Metasound param, it should be called probably declare Metasound param, but whatever. Metasound param under the hood makes a string and all this stuff. And then you forever use input frequency rather than a string, so that input frequency is something that needs to be perfectly typed or it won't compile. So it's like using the compiler to prevent runtime errors for mistyping. It's a bizarre thing about C++. So that's why that exists. So if you curse that boilerplate and you're like, why do I even use it? It's for your own, maybe it's a little bit too verbose of a macro, but it's to prevent crazy runtime errors so that all of your names and stuff hook up properly.
That's always the thing with defensive programming, right? It's like it feels like a little bit of a boat anchor at times, and then you find out, like a game I was working on a while ago was a sports game, and we had the word referee in code. And you know, if you really think about spelling the word referee, and yeah, sure, you'll get it right, but there are many spellings apparently of the word referee, and that's just one of those things where, you know, it might seem like some boilerplate and it might seem like something that you've got to maintain, but then you find a problem without having to do some string comparison, or it doesn't work later, and you don't understand why it doesn't work, and then you put breakpoints in, you slowly go through and you work out like, oh, it never found the parameter because it was called something wrong. Like, you just rather know that stuff really early.
Yes. And the namespace thing, you see that how Dan has namespace TFM vertices. In the OG days, we didn't do that. And then we found we were getting, because Unreal Engine compiles things in big modules. So we're getting name collisions from like node A and node B would have the same name parameter, and they would like swap in the node registry and everything would jacked up. So that's why so there's a lot of weird stuff that came from pain and suffering.
Yes, that's actually a good point. This is to avoid common name collisions.
Which, you know, when you're dealing with things like frequency modulation, gain,
exactly,
you're gonna have all the time. Yeah.
In fact, if you look at the harmonics approach, they actually just did a big declaration in a separate file of all the possible names that they would use, and then they just recycle that.
Which is honestly not a bad idea because, you know, it's less memory.
Yeah, but it's also, you know, the monolithic file approach again. I mean, it's maybe a trivial amount, but it's that kind of idea again.
The other nice thing about that is if you want to change names of something or like do a pass on like cleaning up your tool text, you have one place to go rather than
that's true. That's a good point. Okay, where was I? Right. So on construction, I grab the operator settings and I just get the num frames per block, which is this it depends on your sort of Metasound configuration. The default is going to be actually I think it's 480 in this case, because its default is going to be 100 times per second for blocks. So block rate is 100 times per second, and the sample rate by default is going to be 48 kilohertz. So
you can set both 48,000.
Yeah, these are that's why I need to cache the values, because this could be changed. This could be changed for either by some sort of system or by CVAR, etc. So that is why I cache those values, and I don't.
You could cache the setting struct itself, by the way. That's an option. There's many ways to skin the cat.
Yeah, I just wanted that. I mean, it's so. Here's the thing:
we always cache.
No, but until this changes, I don't think it's going to change anytime soon. Those settings are constant throughout the lifetime of the operator. So they won't be revisited.
All I'm saying is rather than store two variables off, you could cache the whole setting struct and then.
Right.
I'm just saying you could do that.
Yes, but
fine.
those are the only ones I needed.
Yeah, it's fine. You did, it's fine.
And then I initialize my processor, my little FM.
So is your FM generator object defined somewhere else? Do you have a CPP file?
Yes, no, it's up here. I just have it up here under this namespace.
I see. So you include it. You collab. Okay, I see.
Yeah, just to keep everything simple
in one file.
Yeah. When I'm experimenting, it's just easier to have the whole thing in one or two files.
One of the things that we try to do is a node. Like if this was something that we wanted to check in, you would take the DSP code separately, check that in as a separate file. Then the metasound thing is just a usage of that file. So that would get put into a separate CPP file and then included in. The point being is that someone could use that pure FM class in a different node or somewhere else really easily rather than having to extract his DSP class from the node. So in other words, the metasound node is just like the glue code to get it plugged in versus like any serious DSP work. That's the ideal.
Yeah, exactly.
It is worth mentioning that like in this file is several different things working together, and when you make your own metasound patches, you may have more or less, or like dramatically more or dramatically less code than what's here, and definitely something where people get like worried that metasounds are really hard to write. It's like, well, it depends what kind of thing you're writing and when you're referencing other elements, and if you're breaking them into regions, you might find that you don't even touch half this file while you're doing all the DSP, and you're just sort of touching one or two functions.
Yeah, that's right. Exactly. Yeah, and if you want like a really simple audio rate example in the engine, is my first metasound node, which is the ring mod metasound node, which was completely unnecessary because
you could just do it.
You can just do it pretty easily
together.
But I wanted to practice.
We have a multiply audio times multiply as an operator. That is ring mod.
Yeah, but the problem is like, does the person stepping into game audio or coming from a door know that that's what that is? Like, I think Metasounds has that problem of, you could do anything if you know what you're trying to do. So having the helper nodes where ring mod is like, well, I want a ring mod, so I use the ring mod node. Like, that does make sense to me.
Yeah. Which, if you look at the GitHub, you can see a recent node that I've checked in. In fact, just this last week is called the fade node.
Anyway.
Oh yeah. Okay. Anyway, so here's where we're binding our vertices to our cached references in the inputs and the output, and then the reset. This is another thing the reset function is used in case of the operator cache is being utilized. So this should look exactly like your constructor.
Most of the time you can ignore the reset function now, but
no, you can't.
When does reset run?
Reset is run when you retrieve a cached operator from the operator cache. So there's an optimization you can add. Eric, you explain the operator cache.
I mean, yeah. So operator cache. Let's say you have a minute.
Zoom in. Can you zoom in while he explains it?
Is
there a way to zoom in on his face so you can see the sweat?
I've been awake since 3:30 this morning, and now I have to explain the operator cache.
Are you regretting that you agreed to come onto this?
But as Dan mentioned, it's an optimization tool that you can use for caching large metasounds to not have to recompile or rebuild them at runtime. So if you have, let's say, some sound and you want to play a bunch of those sounds at the same time, but you don't want to build them all the time, you can store like a bunch of instances in the cache, and then it will reuse instances from the cache rather than creating a new instance. And so what the reset function will do is when it goes back into the cache, once it's been released and you're not using that instance anymore, I assume that's when reset is called, and resets the operator back to its initial values, so you're not having stale data from previous instances of the metasound leaking into your newer instances.
Yeah, exactly right. So you want basically your reset function to be as an actual reset. To think about it like that, you're resetting the state of your operator to its initial conditions, and the things that can change include the sample rate of your operator. Right. So because it's a new instance, a new Metasound instance, and so the Metasound could have been managed in some way to have a different sample rate or block rate.
So the buried lead on that though is a thing that a lot of people don't know, is that Metasounds are actually compiled on the fly. So when you load up Unreal Engine and there's a like message that says compiling shaders, and everyone hates it, and you're like, well, Metasounds actually also compile, but they're way faster to compile, and we actually compile them on the fly. And so when you go to play a Metasound, it actually will compile right there. In the past, that was actually a bottleneck, but it's asynchronously compiled. But in really crazy situations where you're constrained and you're playing the same Metasounds rapidly, it does show up on the CPU graph. You'll be like, what is this? There's a lot of Metasound compiled. And so the operator cache was created as a kind of solution for that. So you can opt a Metasound in to get cached. So it doesn't recompile it. It just reuses it if it's already compiled. That's the whole idea of it.
Yeah.
Down the road, we want to actually have an option for Metasounds to get compiled during cook, so that the Metasound comes pre-compiled, or have a offline Metasound compile process somewhat analogous to shader compile. It'll be much faster. But there may be a thing in the future where you'll see shaders compiling and then whoop, Metasound's compiling, and it'll be a lot faster. But there may be a world where that happens down the road, so that it's sort of pre-compiled and that all it is a load. The tricky part is the runtime memory has to be kind of hooked up for the graph to operate correctly. So it'll have to be a secondary phase of what's called pointer fix-up. So you load up the pre-compiled Metasound graph, and then like wherever that lives in memory, you have to like point to where the pointers go so that it actually works.
It's like recontextualizing the pointer addresses, right?
Yeah, exactly.
Yeah.
But that's something on our roadmap to add as an optimization. But Metasounds compile so quickly that the vast majority of users won't really notice or care.
Yeah.
Fortnite notices it because we have an army of perfmem people, and we have to run on Switch. So
and mobile, and we have pretty large Metasounds for like some of like the weapons and stuff are pretty,
which are rapid fire, short duration. You can't be compiling massive Metasounds that fast.
Yeah, we do a lot, as much as we can, to reuse instances, even audio components, so we're not spawning new components every time, stuff like that.
Deep dive random tangent, but you know.
Yep.
That's why I'm on, I guess, is to give you guys some background shit.
That's right.
Good shit.
That's right. Cool. And then here's my execute function. Super simple. I just zero out my audio output buffer just in case.
You shouldn't have to do that.
I shouldn't have to do that, but you know.
That's worse.
And then I do a check, which I also shouldn't have to do, but you know, just in case.
If that ever hit, then things have gone terribly.
Yeah, well, that's
terribly wrong.
That's why I put the.
I can't even conceive of when that happened.
Anyway, and then I have my generate function, where I pass in my my audio buffer pointer, the number of samples I want to generate, the frequency input, the feedback input, and then the modulation, the pointer to the modulation data. Because I only have one number, this is why the check is there. If something goes catastrophically wrong, I'll know about it before it hits where I'm supposed to hit. Basically, where I'm basically expected to have these be equal to each other. And then I have linear in, which is the bool. And these are the read refs here down here, which are basically pointers. So I'm grabbing the values.
Well, they're references. They're not pointers.
They're references. Yes. Sorry.
What's funny to me is this is all really boring. This is all boilerplate. The actually interesting work is in your generate, which you've totally boiled over. So can you just go into that function? Because that's where.
You don't want to keep talking about the reset function?
I'm saying I want to emphasize all of the code we've looked at so far is not that interesting. Like that's just boilerplate and hooking things up.
And yet people have learned a lot.
That maybe, but I will say the actual interesting fun shit is in this generate function.
Yeah.
Which is what I'm interested in looking at what you did.
Yeah. Yeah, this is where the real critique comes. Okay, so I early out if I have 0 samples to generate. That's an optimization, right?
Not really. I mean, sure.
Sure.
I mean, if there's no samples, it won't do anything, right?
Yeah, but I mean, it's like it's going to be a drop in the bucket on terms of the performance cost. Yeah. I don't know. It just sure.
Let's look at that bucket.
It's fine. Yeah.
So I create views of the output audio. So this is the audio I'm supposed to generate out to. A TRA view is a nice slice of a buffer. In this case, I'm taking the whole buffer to create this view.
So let me explain TRA view a little bit better. So TRA is actually a regular array in a computer.
Yeah.
Like any array you've thought of, which means it's a pointer and some block of memory, right? TRA view is you can treat it as if it's a regular OL array, but is essentially a offset within a reference array. So he's got somewhere, let's say 256 float array, but he wants to have a subsection of that array or use it as if it's a full-fledged array. So you can get num, you can get 0, you can do all of the indexing as if it's a real array, but it's actually a reference to a different array, which is really important because you don't want to be moving memory around if you can avoid it.
Yeah.
Like copying memory and all this stuff. So the original actual memory, which is where the audio is, stays put. You're not copying it around, but then you have this sort of lightweight object that can act as if it's a copy of the array or a view into the array.
Yes.
So you can have a lot of really nice utilities, avoid writing out of bounds in the logic that you're trying to do. So we have been using TRA view a lot. It's a relatively new container of a container.
Yeah.
A couple of years ago it came out, but anyways, we have it all over our audio code base now because it's extremely useful.
Yeah.
Because it's allows you to do a lot of really powerful stuff without copying arrays around.
Yeah.
But it is just a utility. You don't need it. You can get around without it in some pointer math. But anyways.
It's like a window, right?
It's like a window into the actual array.
Yes, that's the important part. Is that it's not a copy of the array. So here, if you look at, I actually just have a pointer, right, to the, I would guess the head of the array.
Yes.
And then I have the number of samples suggests that this is how many float values have been allocated for that array.
If I were to have written this, I would have just passed in a regular T array, by the way, if you could avoid it. Like generate would be T array reference in audio, and then you wouldn't need two parameters, it'd be one parameter, just FYI. But it is essentially
okay, yes, you can do that. But not all of the you might have to if it you
might have to adapt it to another API.
Yeah.
But the float star is essentially the same as it's like a C array.
Yeah,
it's a pointer to the top of the array.
It's an inference of an array.
Yeah, float star is a pointer to the top of the array. Anyways, the point is he's saying is that you can pass it into the T array view and it turns it into. But in the way you've done this right here, it's a little bit superfluous. As I said, you could have just had a T array for your output there, making a view on it. It's kind of silly, but whatever.
Yep.
I liked it, Dan.
Well, go back to go to the place where you call generate. I just want to make a point. So you call generate, right?
Yeah.
See how you have right there audio out, and then you say get data and num. Yep. What you could have done is just do star.
Yeah, I know. Yes.
Audio
but
out.
But this generate function could also be used in other parts of the engine where you don't already have a construct there. So I'm just saying. There are other buffer
C++ is like a cat skinning. There's so many ways to skin cats.
Cat skinning.
Maybe
is that what the C stands for? Okay.
Yeah, it's a violent way to look at it.
Anyway, I do the same thing for the mod, except this is a const. values. We're just reading from it. It's read only essentially. And then yeah. So then I have some scratch buffers up together. There you go.
So wait,
here you go.
what's
This
this
doesn't
phase
have
per sample thing? That's
Huh?
crazy. What the phase per sample? Sorry, I was looking at your next line. What are you doing there?
So basically I am conceiving of the time index for my sign generation as a function assuming a single second. And so I have a phase traversal of 1 over sample rate. Okay. And then that is a 1 second value. And then I know and then I can apply a frequency to that value. And I will get the phase traversal at that frequency. Is that understood?
Okay, I guess.
So imagine it's if you have like a sine function, it's your x value is your phase.
Is our audience dropping off by now? By the way, sorry, just joking.
Yes.
Yes.
Yes. The answer is yes.
All right. So you got your phase sample. Then
Yeah.
if the frequency changes, that's the next line. If it's not nearly equal, it changes.
So I set up frequency as an array.
Yeah.
If the frequency changes, then then I do an interpolation. So if the frequency started at say 220 and it went up to 330, then I do a sort of one buffer interpolation between those, just to kind of smooth out the shift.
So what you are using here for the 2 people remaining on this call,
there are 5 people.
Okay, 5 people. I'm going to imagine there's 1 million people going to check into this next week.
Yes.
So you're using a really powerful library that I want to highlight.
Yeah.
Can you Control G or step into that array
Which
set?
one?
This one? That guy.
Yeah.
Just step into it and show this thing. We have this. This is one of the benefits of doing DSP in Unreal Engine for audio, because we have this crazy library that we're using, and it's always growing, of like highly optimized like audio and array operations. So if you go into that implementation here, you'll see we've got Intel ISPC if it's enabled. This is a super low level kind of thing. And then all of this stuff is SIMD'd. So it's like SIMD means single instruction, multiple data. So the idea is that like you're doing lots of math in one instruction.
Yeah.
So
it's like batching the math ops, right?
Yeah. So you do like up to, so Intel ISPC, I think, lets you do up to 8 at once.
Nice.
SIMD does 4 at once. So you're doing like 4 math operations for every one. So it's like an automatic speed up, plus this thing called cache coherency. In computers, the CPU architecture is such that when memory is loaded into the CPU, it goes, all the way down to the hard drive, into RAM, from RAM into the cache, the CPU cache, and there's multiple levels of the CPU cache. And so if when it goes to read it, it actually pulls in multiple pieces of data for every read. And usually, so in other words, if you have in your RAM, you've got like 5 floats sitting next to each other and it needs one of them, it'll actually load all 5 next to it. If it's next to each other in memory. And it may use only that one float, and then it needs to go somewhere else in memory, and it'll flush all the stuff it previously loaded, go load something else. And each time it's loading something, it takes time, right?
Yeah.
So if you happen to go and do a read on a float you care about, and then the next one you care about, it's already loaded, it doesn't need to go back into RAM.
Right.
So that's called cache coherency. If all your data is already loaded, then the CPU can be really, really fast. And so audio happens to be naturally cache coherent because it's in continuous or contiguous buffers. So you get a big buffer of audio and you're trying to do a bunch of multiplies on it. It goes to load one of the floats in the buffer with the multiply you want to do, and it goes to do the math, and it's like, oh, it's already right there. It's right next to me.
Right.
So I don't need to go and load it. So the audio buffer is fundamentally cache coherent. And then when you apply SIMD, where you're doing 4 multiplies at once, it gets it even faster.
Right.
So one of the tricks for audio DSP in software is you optimize your cache coherency and SIMD it, and you can be blazingly fast. You can be like, how the hell are they getting away with meta sounds and it's not killing your CPU? It's because we have this crazy optimized library that are using all over the place. Dan doesn't need to give a shit about how it actually works. He just knows to go and use it.
Yes.
And so all of this is really complicated to deal with. It's like under here. But going back to your code, it's like if you go to actually how you're using it, you're like, I have this constant, make a constant. So you add an array. So now that frequency is a really fast setter of a let's say whatever the block size is, 480 samples.
480, yeah.
So 480 floats of 1, just instantly set it. There's other ways to do this, but that's fine. Then he does an array fade, which is basically cross-fading a whole block of memory from a previous frequency to the next frequency by some parameter here.
Yeah.
And what was
and interpolating between the two.
It's interpolating this big audio rate block.
It's basically what it does is the array fade multiplies the basically it has this value interpolated between the start and end value, and then it multiplies those against the value in the frequency buffer.
So now it's a 480 buffer of like a ramp. So think of it as like a big ass ramp. So it's like 0.2, 0.201, 0.202 in this like sort of ramp through the buffer. And then the coup de grace is line 82. If you just scroll down, he does this like really fast multiply of that whole thing where it's like this big buffer and another big buffer and just multiplying together. Oh, this is actually in a multiply by constant.
This is in the linear. Yeah, it's basically taking my Nyquist fraction, which is as I mentioned before, a sort of smaller constrained range of my sample rate, and then I'm applying that. Basically, what I'm doing is I'm taking the mod value, and I'm multiplying it against this constant, and then I am feeding that into this buffer here.
So he's taking that whole array and multiplying it by a constant.
Yeah.
Yep.
Which I guess if you weren't doing it with these library functions, that's quite a lot of math. If you really
it's a lot of for loops, I'll tell you what.
For loops and iterating, and so when you find these library, is this just something where you look into the library for every part of this that you're interested in?
Yes. So the way that I do it, so people at home, the sort of Dan's, because I'm not going to like search through because there's a lot of stuff in there, right?
Yeah.
So I try to figure out what I want. And I go audio, that's the namespace, and then I type array, and then I can search through a little bit better, And then I might add like, oh, I know I need to do like an add function, and then we see what it's sort of a menu, right? This is, by the way, ReSharper that I'm using here in Visual Studio.
But even a different answer is go look at some other code and see what they've done.
What they're doing, yeah.
The other one is to just do it the naive way with the loops and just
which I've done here.
Don't give a shit. Yeah.
And here's where I do that the logarithmic transformation. So this is like the nonlinear mode. So it's more expensive here.
So mod is an array, right? Is that
mod is the input value that's coming into the modulation.
But it's an array of floats.
Yeah, it's an audio buffer.
So here's a pro tip. This is a subtle thing. This is why you're here for the call and why I'm here. This is an interesting thing of Unreal Engine. You might see this in a lot of audio code where, like right before this, Dan, and before you do your for loop, like on line 8, just on line 85.
This part.
Yeah, do a new line.
Okay.
I'm just giving you like a
sure. What we got?
Type float star mod PTR.
Okay.
Equals mod dot get data.
Yeah. Oops.
Okay, so what often I don't know why this because it probably needs to be const. Is it?
Oh yeah, it's const. Sorry.
So, by the way, that's another thing. You go like, why is it? Oh, yeah, that's a constant. So that just means that you can't touch the data inside of it. But anyways, so then in your loop, instead of doing mod array I on line 90, type instead of right there where it says mod, write mod PTR. Instead of mod, yeah, and then do your index I.
Like, oh, index I. Oh yeah,
Yeah.
okay. Well, that's cool.
Right there, nothing's changed, but you've sped this up tremendously
Oh, interesting.
in non-shipping builds.
Yeah, that's pretty good.
And the reason
You know?
why every index lookup in our regular T arrays does a whole bunch of math to validate your index isn't going out of bounds.
Right, right.
So what this is like, trust me, bro, I know what I'm doing. I'm looking up this array. Fuck off, you know? Because otherwise, T array is like, because you'll get those errors like, oh, indexing out of bounds. So this is dangerous because you could be writing off the array.
Right.
But you've got mod.num right there. It's
Yeah.
fine.
So
it's like
I'm
it's
sure
like,
I'm sure that it's yeah.
Yeah. So this is essentially going like fuck off with your array checks or boundary
Yeah.
checks.
Right.
And this is we're talking 10x speed up in
Really?
non-shipping builds. Yeah.
Interesting.
Shipping builds, all of those checks get stripped anyways. So shipping is way faster. That's one of the reasons why shipping is fast, because every array in the engine stops doing boundary checks in a shipping build.
Right.
But for audio DSP, when you've got a tight loop and it's really clear, you're not going to do an array bounds issue. This is a like pro tip on speed up. So if you'll see a lot of our code does this, by the way, if you go look at our libraries, and you know you'll go, why are they doing that? That's why. It's because the bounds checks are really, really expensive.
Yeah, and I'm sure that's that's one of those death by a thousand cuts kind of thing. You know?
No, it's when I was doing the audio mixer, I went and did a pass on that, and it was like because people internally at Epic, and I guess most game devs probably are running the game not in shipping build.
Right. Yeah.
And so it makes a difference.
Yeah.
To like not have all your DSP doing bounds checks. You know?
Yeah, you can do that here.
Yeah, that's a great tip.
Cool. Yeah, that's awesome. So yeah, and I probably and I could probably do the same thing here, and then if I wanted to be safe, I could add a check for the num that it's equivalent.
You're doing a mod. We're doing .num.
No, I'm just saying, like, if I wanted to be safe, I could add a check outside of the for loop, and at least it would be.
My philosophy is be safe, but don't be stupid safe.
Okay.
Like, there's a lot of wasted effort when you're like, it's like there's a point of where you're paranoid. You know,
Yeah. Okay.
Don't be paranoid.
Okay. All right. Anyway, so yeah, so this is this function get log frequency clamped, which I wanted to use as a convenience. It only accepts positive input, so I do an absolute value on the input, and then I multiply it against sign, which is a function that returns 1, 0, or -1 based on the sign of the value. So I sort of reclaim my sign outside of that function range, yeah. So then we're back here, and then this is an added. Again, we're using the array utilities. I'm just adding my modulated frequency value to the frequency.
Yep.
So it's basically a modulate, it's an offset. And then I have I basically do the phase modulation here. So I take the phase. Remember this? Where was I here? This thing that you asked me about, phase per sample, and basically do.
So you use that phase per sample way down, right?
Yeah, I'd use it down here.
I would declare it closer to where you use it, FYI.
Yeah, I mean, it used to be closer, and then all this stuff was added in between.
All right, well, put it closer.
Okay.
I'm just saying, like code.
Yeah, I know. Yeah. There we go.
It's a good tip in general for any folks watching.
Get a huge ass file. Like put your stuff.
It's not that big. Anyway, so
it's already. I already forgot what we're doing. Like I don't even know what the hell is going on.
Well, what I'm setting up is this what we asked about. So the frequency is a multiplier against the phase sample. The phase sample represents one sample, right? The phase traversal over a second, or 1 hertz, and then I'm multiplying the phase sample against the frequency. the frequency is modulated, so the frequency changes every sample potentially. And so I am creating a buffer of that I just called phase sample.
Yeah.
And then I have a feedback value that I mentioned before.
Can I
clamp.
complain? Can I
Sorry.
complain real quick?
Yeah, complain. Like
About
you haven't
our own
already.
goddamn API.
Oh, okay.
So array set to constant in place, lowercase p. Array multiply in place, uppercase p. Jesus.
Yes. Well, here's the thing: is that we have
like stuff like that annoys me. That's like this nice clean API, and then there's a freaking ridiculous typo. Why is it
now?
that way?
Well, there is a perforce history, so we can find out why that's the case. But this is what you talked about before. You talked about before about like typos, right? Because the problem with typos is that typos are like systemic. They like once someone typos something once, then like auto, complete like just it's a mess.
What was the
forever,
thing you were
right?
talking about, David? The misspelling of
well, that's the problem, right? When you try and fix it, then your name gets plastered over 65,000 files when you do an auto replace, and then you just take.
This is going to be a huge pain in the ass. It's going to be like a huge changeless because how many times array set to constant in place. But also, you end up going, fuck it, we'll just misspell it. What was the word? The
place. P.
Referee.
Oh, referee. That's
so I guarantee through most of the code it's misspelled, and then right before it gets to the end user, somebody just like swaps out the misspelling to like the correct spelling. It's like
everything breaks.
You've got those macros. What are those macros in Unreal that used to be known as this, and now it's known as this? Just the types for changing things.
Anyway, so the feedback was because it's okay. So the feedback, because it's one sample offset, has a sort of filtering effect. And so when I went to 100% feedback, it just the signal just disappeared. So I just sort of clamped the range because and remapped it because I wanted the 0 to 1 value to feel like there was something you got out of the full range of input, but I wanted to constrain it. So that was the idea with there.
It is weird. Why is 0.86?
That was the value that I liked. Yeah, that's a good question. When I did my experimentation, I liked that as the limit, the upper limit. I didn't like going above that. That's why.
I like to imagine you testing 0.87 and going, nope.
Nope.
No right.
way. Absolutely not.
That's right. Okay, so where was I? Right. Okay, so then here we go. Here's the clamp feedback. Basically, they're doing a very similar thing as the as I did here. So I'm just taking that value.
I just noticed something. Why did you do 0.5 times 0.5? What the fuck? What's going on there?
Where were? Oh, because so this for this.
Yeah,
guy?
I just saw that. We skipped over it, but like, what? Why? What?
So because it's a Nyquist fraction. So this is Nyquist.
Oh, that explains it.
And this is the amount that I tried for, and I could make it a const, and play around with it. But it's just sort of I just was like, oh, give me half. I started with 0.25 and it wasn't enough. That's basically what happened. Is I sort of like,
what? That is 0.25.
No. I started with this being lower. I started with like that.
Oh well, you could replace
like a quarter of Nyquist
times 0.5 by 0.25. I'm just the compiler will do that anyways. It's just weird to see.
No. I know. For me, it was this was Nyquist, and then this was the fraction. That's how I saw it.
What you're trying to say.
So I could have split it up into different values, or I could have made this a const, or something. There's lots of different.
Const float Nyquist sample rate times 0.5.
Yeah.
That's what you're saying.
Anyway,
that's where a comment would be helpful, by the way.
Yes. Yeah, that was actually something I was going to bring up. Was as always comment, unlike what I have done here. I've done no comment
in any of this.
But yeah, yes, there should be comment all over. There should be comments all over the place. I totally agree. Because there isn't a Dan for every code review. So that's the. Anyway, this is just smoothing it out. Like I said, the feedback could change, and I want to have like an interpolation buffer. So that's all that is. And then this is the actual function that does my modulation. So here's my output. I get the current phase times 2 pi because it's a nice little circle cycle. And then here I calculate the feedback sample amount, by multiplying the output. This is what I said was sort of one sample offset. Current phase, by the way, starts at 0 and goes to goes to 1 here. So here we go. But this output will multiply against frequency mod times phase per sample times the feedback amount.
So that's the magic. There's the magic.
And that's just the feedback.
So why are
sample
you
amount.
not doing that in a SIMD?
Okay. And then I have a modulo function.
You just ignore me. I'm just saying you got
I
all
haven't
this
learned how to
crazy
do that.
SIMD library shit, and then you do a fucking loop, and I see some math in a tight loop here. Output I times frequency mod I.
Yeah, but you don't have any trig functions in that library.
Well, the trig maybe, but the next line.
Well, this is dependent on the output. It's a feedback. So I have to take the... Huh?
Couldn't you stuff the sinusoid into an array, then do the SIMD there?
Sure. Okay. I mean, it's... I guess...
I mean, that's the trick of SIMDs. You put everything in arrays.
No, here's the no. I couldn't do that. No, because here's the thing.
Hold on a second.
Yeah, this is a feedback.
You're right.
So it's just and then the feedback affects the phase traversal.
Yeah. Okay, so this is a good point. When you do feedback, you suddenly can't do SIMD. SIMD is one of the things that's hard to you simply can't do it with feedback. So certain DSP applications where like the output of the next sample depends on the previous one, you can't break it up in SIMD. So,
but that is also
your honor is restored, Dan.
But that is also the case for the phase traversal for the frequency modulation. Even if I didn't have the feedback, I would still require a loop for this because the phase sample is variable, and it depends on the phase. So incrementally,
is the phase sample variable, or does it just step through the phase over?
No. The phase sample is the phase per sample multiplied by the frequency, right? So the frequency changes every sample, every buffer.
Yeah, but you could still. The fundamental issue is this feedback that you have, the feedback sample amount.
I'm saying that even without that, you would still have non-linear loops. You couldn't just call a sine function. The value would change. I mean, you could build this.
I get
build this.
saying.
You know what I'm saying? Like that's So
but
it's fine. Just one of those still cache coherent.
Says that you can't do this because it's feedback, and that's why that this is there.
Exactly. Yeah. But going back to the get data trick, I would put get datas on all these index lookups.
Yeah, I like that idea.
That'll speed it up for non-shipping builds. But.
Yeah, no, that's great. And then I just do a simple update on like my cached values. These are the values that I interpolate if they change.
The other speed up that would help you is to consider a sign approximation. So you're using raw.
I wasn't sure how that would affect the timbre, and so I sort of.
You could try it. I think it'd probably be fine. But anyways, so this is a big thing for the listeners if they're still here. Is generating sine tones using pure math is actually kind of expensive. It's not as bad as it used to be, or so I'm told. But fmath sine goes to like low level math library, and it's like scientifically precise sine wave generation, and that's computationally expensive. And so we actually have utilities for sine wave approximations. If you go to Dan, do you actually have the editor open still?
Yes, I do.
Yeah, so if you pull over the editor and go to, so this is an explanation of something that's in Metasounds. If we still have people listening.
This is in the oscillator.
Just make a new Metasound. I just want to show people this thing. If you go to,
there we go.
Yeah, if you just type sine.
Yep.
Down at the type there, we have 4 here. There's even more. These are sine wave approximations. So pure math is the like thing that Dan just used.
Yeah, most expensive.
And it's the best, but it's the most expensive in this list. But then we have other approximations. 2D rotation is a fun one that was new to me, where it actually computes a unit circle and it like does this vector rotation, which is kind of cool. pretty fast. And then my favorite is the Bhaskara. If you look at that,
Right.
that actually would be fun to listen to it. You like hear it, like what are the different approximations? So Bhaskara is this like 7th century like crazy Indian mathematician or something, came up with this awesome sine wave approximation, which is really cheap computationally. They all, and then of course wavetable is you compute it using pure math and stuff it in a table, which has downsides. There's downsides.
Yeah.
So
Aliasing and stuff like that.
but anyways, this is a big deal for computation. So actually, Eric, if you
Well,
wavetable is actually pretty cheap, but if you are using sine waves, consider some of these other ones.
Yeah.
As you know, look at their CPU.
Well, hold on a second. I think this is something important is to mention is that the 2D rotation does not support frequency modulation.
It doesn't?
No, it does not support it. So
I did not know that.
glide and FM doesn't work with it.
Oh yeah, glide and audio rate. I guess
Yeah.
So don't worry about. Oh yeah, because 2D rotation depends on fixed frequency.
Yeah.
There's another one that's similar, which is this resonant sine tone generation, which we don't. We do have that in the engine, but it's another classic cheap sine wave technique. But it doesn't support changing frequency rapidly.
Well, if we end up bringing this FM oscillator over to the actual engine, that's definitely something we'd want to implement
for node config.
Different sine functions, wave functions.
When we get around to re-implementing sine, we're probably just FYI, we're going to probably make it an oscillator object, and then with node config, you'll be able to select what type of oscillator and what kind of approximation you want to use. So we'll change that in the future. But just FYI, it's a whole big topic of sine wave approximation.
Anyway, so this is it. This is this is everything. Saw everything. So that's it.
Nice.
Yeah.
All right,
Kind of doing a lot when you think about like how much DSP stuff that you actually have going on. It sounds pretty great. How much you can get out of it.
That's
Given that it's not that much DSP.
It's actually simple. Quite simple.
Yeah.
You know, conceptually it's simple. Obviously, there's sort of some finicky aspects in the details, but you can get a wide range of timbral outputs with even just as I sort of showed, like 2 or 3 operators. Imagine then going something like DX7 where you have 7 operators, or the like FM8's a popular that's from Native Instruments that has 8 operators.
The hard part of FM synthesis isn't the creating the FM or PM synthesizer. The hard part, which we don't have to do, is to like come up with a mathematical explanation of the crazy timbres that are created when you put it through. It's like understanding or even predicting, like if I do this to this to this, what's the outcome? Like that's where it gets hard. But like the implementation of the lower level is actually the easy part. It's like, which is famous, by the way. Like John Chowning, one of the guys who invented, I think he actually did invent FM synthesis. I actually got to meet him a couple times, and he said exactly that. Like it's actually trivial. It's a really simple, extremely cheap synthesis technique, but the difficulty is like using it as a modeler, like to how to model sound or predict or come up with something.
It's not like particularly intuitive. You're not like, this needs a bit of square. It's very hard to have that intuitive. It's not like grabbing an EQ and going like, a bit of brightness here.
It's not additive synthesis. So additive synthesis is the sort of like analog to like FFT. And FFT is like you take an existing sound and you break it into sine tones. Additive synthesis, you take those sine tones and add it back. Like that is a very intuitive mathematical understanding to model sounds.
Or even subtractive. It's different from subtractive in the same way.
Subtractive is very intuitive. Yeah. Noise with a filter,
Yeah.
FM synthesis gets into the weird range where you're like, what the hell does this even mean? In terms of like, I want to make an oboe. And it's like, okay, how do you make an oboe with FM synthesis? And you're like, I don't know. Yeah. Like that's where it gets hard. How do you make a cool, crazy alien sound with FM synthesis? I don't know either, but I can combine it and have fun.
The alien sounds are a little bit easier to achieve.
Yeah, exactly.
Because of that. One of the things that I have noticed, I think this is I probably even read this or learned about it, similarly, but it's just that having the operator frequency relationships be harmonic multiples or divisors, tends to result in a more musical tone.
Yep, makes sense.
So, yeah, you'll see. In fact, if we look at my patch here, the test base, I stopped sharing here. Let's see what was that. Oh, maybe I didn't. Oh, yeah. So yeah, here I have this operator is twice the input frequency, and this is half the input. So this, yeah, and being over the frequency of your like the operator you're modulating has a different effect than if you're under it. Yeah.
Can you demonstrate that?
Yes. Yeah, I can. So if I go back to my little demo here, and we have, let me just get rid of the modulation. So here we have, oh wait, I have feedback, sorry. Here we have a simple tone, and then let me get rid of the feedback here, and we'll add the modulation. This is under, so this is about 10 times less. And as I go up, now when I go, look at the waveform if you can see it. When I go over, you'll see that it's actually like more like the original signal with little wigglies on it.
It's like wave shape.
Yeah, a little bit. It's hard because this isn't tuning itself to the frequency that we're observing. But yeah, anyway. So it might be more obvious if I lower the original one. So here's under, and then here's over.
Gotcha. Okay.
And you can kind of see the kind of bands that we get when we're under compared to when we go over.
Yeah, it's crazy.
Look, see how the original signal pops through. See that?
The strong signal.
The strong one, and that, yeah, exactly. And then because you can't see where I'm pointing on my screen, then we go down, and it actually kind of disappears.
Yeah.
So, yeah.
I mean, this kind of stuff is like really hard to predict, though. Is like given this frequency modulation range with this mod index with this kind of thing, what spectral output do you expect? That's really hard to characterize mathematically.
Yeah.
Because I mean, there's just so much destructive and constructive
Yeah.
interference in the signal that you just get.
There's a lot going on. Yeah, and then you can imagine how and then if you have something like a complex system like the DX7, where it's like, oh, you have 4 operators deep.
Yeah.
What is the result
Who
of
the hell
that?
knows?
Yeah, with feedback, and it's just like
Which for the DX7 like sound designers and those folks like from Yamaha who put that stuff together, there's a lot of work to kind of figure out like cool sounds, like the bell sound and or the whatever sound, and you like get those presets in. That's some crazy brain shit to like put that together to like actually make FM synthesis usable at a pop level,
It feels like the naive implementation is that you have a button that randomizes every parameter, and then you just hit it until you're happy with a sound, and then you write down the preset, and you go like, great, moving on.
But I would say that FM synthesis is harder to do that in, because I would say a large portion of it just sounds like aliens.
Yes.
Whatever.
Yeah.
It's like 99% of the parameter space is
the fact that they can get musical tones and
that's what I'm
nice,
trying to say.
nice textures out of it, and you're like, how?
Yeah.
That's where studying patches can be really helpful. So if you're like, oh, I can study the patch. And sometimes people write papers on patch, algorithms or particular patches. Like I've read articles where it's like, here's how you get that 80s brass sound with FM, that kind of thing. And then you have like a starting point, and then you can sort of branch out, and it's easier to sort of explore from something that kind of works.
The other big breakthrough in FM synthesis, which is one of the reasons why it took over, why Yamaha got big into it, is that before FM synthesis, digital synthesis was prohibitive because of how expensive it is to do through additive synthesis. So like analog was pretty much the only way to do it. Like build a raw synthesizer and a filter, which is expensive. Digital filters are expensive. All of that kind of stuff was like really analog, like to really Moog and all that shit. And then when FM synthesis came out, Yamaha saw the potential from a optimization standpoint and they just like crunched through the math, and like with a 3 or 4 oscillators, like really cheap, you could do the kind of thing that would be like freaking crazy computationally expensive with filters, the equivalent through subtractive synthesis, or it would maybe not even be possible.
Yeah,
so it was like a story of digital optimization too.
Yeah, you can see my bass patch as an example. I use an envelope to increase or decrease the amount of modulation.
Yeah,
and that is almost like modulating it, but there's no filter, right? The effect is like almost like you had a filter,
like a filter. That wow. No filter, zero
no
filter.
Yeah.
So it's therefore significantly less expensive computationally. Filters are just really expensive.
Yeah.
It's like the order of expensive shit is reverb is really expensive. Filters are expensive.
Yeah.
Synthesis, like sine tone generators, is expensive.
Decoding audio.
What?
Decoding audio.
Yeah, decoding audio is like synthesis, and it can be expensive. It's more expensive, obviously, to decode audio than play a sine tone.
Yeah.
By a lot, but decoding can be thought of as like a really fancy synthesizer. Is the way I would think about decoding. That's what you're doing. Like when you take an encoded audio file and decode it, you're re-synthesizing it.
Yeah.
So it is synthesis. That's why in Metasounds, the most expensive thing you can do is play a sound file. It's, for real. Like that's the most expensive thing by far.
So all we need to do is just make every sound out of FFT instead, and that'll be faster and easier. Yeah.
Or approximate everything with FM synthesis.
Yeah. Yeah, exactly. It could be a huge optimization. We just do everything. We can do a Fortnite mod where it's just all FM synthesizer.
I would love that.
Everything's just FM synthesis.
I don't want to do all of the work. Someone else should do that. But I like the idea a lot.
I like the idea of it, yeah.
Turns into like a freaking DX7 patch. It's like you're gonna get copyright struck.
Yeah, that's right. Because my vocal reproduction is so spot on.
Well, one thing we didn't mention on this is that David is in Australia and we're all in Washington, the rest of us. So, there is an hour difference, and I want to say thanks.
An hour. That's right. There's an hour difference.
Is it 1 hour? Actually, what is the time difference?
I mean, it's 1 p.m. on Friday here.
Yeah.
Wow. On Friday, you're in the future.
Yeah. I'm in the future. I've already finished. I've already made. I thought we were making the Fortnite FM thing, so I've already done that. You guys are gonna love it tomorrow.
We are 8 p.m. on Thursday. So what's the time? So God, that's a lot of time.
It's ages, yeah. So when I work with US companies, I usually start 3 a.m. here, which is like 10 a.m. your time.
That's the worst. The worst.
That's how is that even possible? Like, so I'm trying to show. So you said it's 1 p.m. there.
So the Earth is
13 plus 4. That's 17 hours off.
Yeah, the dateline starts in New Zealand, or just slightly off in New Zealand. So you're just on a really opposite end of the dateline.
Yeah. Wow. The Pacific is really big.
Yeah. It turns out.
Yeah, it turns out.
And it's the other way around it too. It's like the long way around. Anyways.
Yep, that's right.
Cool.
Yeah. So yes,
from the future.
Yeah,
no, it's great. I mean, thanks for the demo. The demo is great. Like being able to talk. I know through some of the stuff is low level, and some people don't. It doesn't vibe with all of it. But I find that as a reference, talking about some of these things is pretty hard to find some of this information and to talk at length about why it's important. So I think a lot of the stuff there is really, really interesting. And I mean, I just can't get over how cool just turning up that feedback knob just suddenly sounds so cool.
Yeah.
Yeah, we got to get that in for the masses.
That'd be fun. That'd be fun
for your fans.
That's right. Yeah. Well, so we're at time. Thank you everyone who joined.
I'm ready for bed.
Especially for the folks who stuck it out the whole time. You win a special award. It's Angel Lights 6 a.m. there. Nice. So yeah, some people are in Europe, which is crazy also. really appreciate your joining us. And yeah, thanks Eric, Aaron, David.
Yeah.
For
Thanks
really
for having me.
making
As
this an
always.
awesome stream. Yeah.
Awesome.
All right. Thanks everyone. You have a good night.
All right.